In this video, we're going to talk about collision theory. In order for reactions to take place, the reacting particles, have to collide with each other. Okay? So that's the most important thing. If they don't collide with each other, they can't form products. But it's not enough that they just collide. They have to collide with enough energy. So they can't just kind of like bump into each other. Most of the time, they have to kind of slam into each other with an awful lot of energy. This just enough energy to get started, you've learned, is called the activation energy. Okay, so activation is the energy just enough to get the reaction started. Okay, and I'll show you on an energy diagram kind of what that means. But not only do they have to collide and with enough energy, they have to collide in the correct orientation. Okay, it may be that they need to collide end to end or side to side, and if they don't collide exactly right, then they won't react either. This correct orientation is called the transition state. Sometimes it's called the activated complex. I think I'm probably always going to call it the transition state. Okay, so anything that we do that can cause more collisions, okay, or more effective collisions, okay, an effective collision is any collision between particles with enough energy to react. So anything we can do to increase collisions and effective collisions will increase the rate of the reaction. Okay, so at the very beginning of this chapter, we looked at things like surface area helped, temperature, a catalyst, and things like that. Okay. So here's an energy diagram where we graph the energy versus the reaction pathway. Okay, and you've seen graphs like this last year. All right, we start here with the reactants. In this case, the reactants are CO and NO2, and the products are CO2 and NO. Okay, this hill right here, okay, this gives us the activation energy. When we say that they have to collide with enough energy, it's enough energy to get up and over this hill. Okay, so the amount of energy they need depends on any given reaction. This one, the particles need to collide with that much, the activation energy. And then once they get up here, they'll only react if they collide in the correct orientation. So we're going to kind of do some Lewis structures here. You would never have to draw an activated complex. I'm just kind of showing you what this might look like so you know what I'm talking about. So CO, we know that has a triple bond, right? Okay. And then it has to collide end to end with an NO2 molecule, so a single bond and a double bond. And maybe you can imagine, in order to make CO2 and NO, this bond is going to have to break right there, and you'll get your CO2 and your NO. And then they just kind of fall down the hill and you've got your products. Okay? And the difference between the reactants and the products is called your delta H, your enthalpy of reaction. This is for an exothermic reaction, so your delta H is negative. Okay? What I'll do on the next page is show you what it looks like when you have an endothermic reaction where energy is required. So again, we'd have your energy, okay, and your reaction pathway. But now if it's endothermic, the reactants are lower and the products are higher. So I'll just do generic reactants and products. So where on this chart is your delta H? Well, delta H is always between the reactants and the products. Okay, it has nothing to do with the size of the hill. This is your delta H. And in this case, it's positive. Okay, this is for an endothermic reaction. Okay, now how do I find my activation energy? Well, the activation energy is always from the reactants to the top of the hill. So this is your activation energy. You'll notice for endothermic reactions, the activation energy is large. It's larger than delta H. Okay, so that would be for an endothermic reaction. All right. We also looked towards the beginning to see what would happen when we talked about catalysts. Okay, so if you remember, a catalyst is anything that speeds up a reaction. Okay, so it's going to make it go faster. That's not a word. That's okay, close enough. And what it does is it does that by decreasing the activation energy by making your transition state more stable. Okay, so what the heck does that mean? Well, it's actually, let me finish writing it, and then it's pretty simple. If we look again at that energy diagram, okay, reaction pathway, so I'll do like this, reactants, product. This would be for a reaction with no catalyst. Okay, and a reaction with a catalyst just makes the size of this hill smaller. Okay, so it would follow this pathway instead. So this is with a catalyst. So what it does is it makes the activation energy less by making the activated complex or transition state more stable. That's all a catalyst does. It gives it sort of a place to react. Temperature is a little more complicated, so that is in the next video, and I'll see you there in a couple minutes.